So this is part two of a survey on blockchain. Here we're gonna go over some development on smart applications, smart contract applications. And so there's a couple of ways you can build a smart contract application. So we're gonna go over two methods. Sorry, we're gonna start with deterministic blockchain applications. So a deterministic application relies on the program's input to determine its output. Deterministic smart contracts ensure that given the same input and conditions, the contract will always produce the same outcome. An example is a random number generator using hash values. So this will produce a deterministic yet unpredictable hash value. So think of it as it's everything executed within the program, so you're not going out connecting to APIs, but we're going to go over that in just a second. But to deterministic blockchain applications, so let's look at a code snippet here on what we're talking about. So here you can see we start the class with contract and Solidity. So the class is a random number generator, or the contract. The function is generate a random number. Uint is it's an undeclared integer. So this is extremely important and common integer type. Can store non-negative integers. It's very common in Ethereum. So use block timestamp and call it address as deterministic inputs. So here we have our parameters highlighted: block timestamp, message sender, and seed. And we're going to hash that input with keycac 256. This is a cryptographic hash function that's native to Solidity and Ethereum-based smart contracts. It's based off of SHA-3, which is used in NIST, National Institute of Standards and Technologies. And so there are many competitions to develop new secure hash algorithms, and this was one that really standed out. And so Ethereum is now using this as de facto method. So we put this hash input into another variable called hash result, so we can convert this hash to uint 256. And that's the hash result, and then we can return this random number, and that's all confined within the execution of the program, so we're not going out at all. Yep. So there's also non-deterministic blockchain applications. So by definition, a non-deterministic output is something that the program cannot guarantee that the input will have predictable outcome of execution. In other words, the program can produce different outputs for the same input. So non-deterministic contracts may rely on external data sources or oracles to make decisions. These external data sources could introduce variability into the contract's execution. For example, pulling a comparison between Ethereum and Bitcoin, or a real-time baseball score. And sorry. So there's the non-deterministic blockchain application. So here we're going to use what's called Chainlink. It's a blockchain application that uses an oracle. So what you need to do first is determine the external adapter. So enable Chainlink node to retrieve data, process it, and return it in a format that can be used by smart contracts on the blockchain. You'll need a Chainlink node. So you have to be on the network, on the Chainlink network. The node will then be responsible for passing the API key and the URL data to the adapter. The adapter would then make the HTTP request. It's a GET request with the API key included in the header. The API key and URL are retrieved from the environment variables. We're going to see some code on how to do that. And so what you would add in your environment variables are the actual export keys, which we've created to get a basketball score. So there is a paywall for real world scores. So this was a score on 12/2/2023, but you should be able to pull real world data if you're willing to pay for that. And then there's the export API key URL. So looking at the code here, you retrieve, so you add a constant variable for the for the environment variables. And you define the adapter with the HTTP GET request. And so, so this is how you do that. Okay, so moving on to reentrancy attacks. The reentrancy attack can manipulate the control flow of the program by whomever was the callee of the program, essentially allowing them to be the caller. The attacker or caller can then repeatedly call the withdrawal function and empty funds. So here you can see this is the one function reentrancy attack. So you can see that the issue. So the issue here is we're running the contract and we're running this withdrawal function. And so this will use the external call to transfer the ETH to the message sender. Then the user's balance is updated after the external call. A fallback function can be used to keep recalling the withdrawal function since the user balance mapping isn't updated until after the call. So that's what's highlighted right here is the balances messenger equals 0. So that's an update. So since you updated, the reentering invocation of withdrawal can repeatedly withdraw the designated balance, eventually depleting the smart contract of its total funds. So one fix for this is adding the balance mesh sender update up in the function. So will be no way to recall the withdrawal function again without the program knowing that there has already been a call to the function because of the update. However, if another function were to call the withdrawal method, then the same type of attack could be used. So so this is the fix for use one function. But if you were to use cross-function reentrancy attacks, then the reentrancy could still be a potential threat. So this is known as cross-function reentrancy, arising when multiple functions share the same state. So the balances mapping in the contract is used to keep track of the balances of each address in the contract. Each Ethereum address serves as a key mapping associated value in the balance. So as you can see here, the attacker could initially call the withdrawal function. The withdrawal call hasn't yet concluded when the attacker re-enters via the transfer function by accessing the mapped parameters. So the attacker can then transfer the incorrectly managed balance from the transfer function to an address they control, thereby repeating the process with that address, even though they've already been received their withdrawal amount properly. But so you can keep this attack could keep recurring by essentially looping over the withdrawal function we're reiterating over it until the funds are depleted, because you wouldn't be able to hit this update, balance update.